Welcome to Unit 2. This is going to be by far one of the most important units that we're going to cover in this class. We saw in the previous chapter that when we pose some kind of linear equation, our job is to try to find out what values beta 0 and beta 1 have to take to come up with an estimated equation. The estimated equation being to the right hand side. The method that we're going to use to find the values that best describe the relationship between x and y is something called ordinary least squares, or OLS, as is in the title of the slide. And what it does is that it minimizes the difference between the actual observed value of y and the predicted value of y given to us by our own equation. This is what graphically this is going to look like. Don't worry right now about the mathematics or the graph, because we'll look into these things in greater detail later on. But you can see here the three things we're talking about. These points mean data, coordinates between x and y. This solid line is the true line, the one we're trying to estimate. And of course, the dashed line is the regression line. The distance between a data point and the estimated line is what we're going to call the residual sum of squares, represented here by this difference between an observed value of y and a predicted value of y. Why are we going to use OLS? For many reasons. One, it is easy to use, and practically in every software that deals with statistics or econometrics, OLS is a click of a button away. Since we're going to minimize that discrepancy between the observed value and the actual value, the residual sum of squares, using OLS becomes intuitive and theoretically appealing, as we'll see through the chapter. And the OLS estimates have a number of useful characteristics that we're also going to talk in greater detail during the chapter. Once we're done with that, we're going to come up with specific equations that are going to allow us to come up with numbers for our values for beta 1 and beta 0. These formulae are only going to work in the simplest model possible, the model when we only have one explanatory variable right here. So when we have a single linear model, these are the equations that we're going to use. Again, don't worry about these equations. We all are going to work them out through the lecture, and you don't have to memorize them right now. When we expand the model to a multivariate model, as we'll do in the second part of the chapter, these equations are no longer going to be useful, and we're actually not going to need any equations. The computer is going to provide us with the actual values. But we're going to be able to come up with models that have more than one independent variable. In this case, this is a model of financial aid received by a student as a function of the amount of money that the parents have and the high school ranking of the student, under the idea that financial aid is both need and merit-based. This is a purely theoretical representation. You might remember that from the previous unit. This is a stochastic representation. I have a specific functional form attached to it and an error term. And this is an actual estimated model, where I observe here a negative relationship between financial aid received and the ability of the parents to pay, just as I expected it here, and a positive relationship between high school rank and financial aid, merit and need. In the last part of this chapter, we're going to be looking about what makes a model good. One of the first things we're going to look at is the so-called goodness of fit. And that basically means how well is my line going to track the data. Good like here, or not so good like here. For that, we're going to use different metrics. The first one is called the multiple coefficient of determination, also known as R squared. You might remember that from statistics class. Then we're going to look at the problems of R squared and its solution called the adjusted R squared. And lastly, we're going to be looking at what conditions we need to have to be able to compare models. That is, if I have one model and another model and I want to know which one is better, there are certain conditions that I need to make sure I'm satisfied to be able to compare apples to apples.